Good morning, everyone. I'm Sweet Tea Dorminy. I work at Meta for the past year and a half working on Btrfs. In particular, I've been working on adding encryption to Btrfs to provide a better subvolume security through our fleet. Before this, I worked at Red Hat working on Device Mapper. So I've been in the kernel space for something like 9 years now. I really like storage or something like this. Fortunately, this is low level enough that I don't have to deal with that technology that likes to malfunction. So hopefully I can pull off making slides come onto the screen. But you know, technology. I'm going to be talking about how Btrfs is used at Meta for our containers. I'll be talking about existing encryption options that you can use right now. Then I'll be talking about the new stuff that comes about when we add encryption directly to Btrfs, and also the future stuff that I hope to add to Btrfs in the future one day soon, real soon now. So let me tell you about how we very roughly do things at Meta. We have, as everyone knows, millions of machines running all sorts of services. I hear that we like microservices or something. Our usual practice is to have one subvolume per service. We then package up the subvolume into a container, run it isolated from whatever else is running on the system. We initially generate that subvolume using Btrfs send receive, which is a really cool technology that Btrfs has. We have Antler 2, which is a program that takes a stuff. I don't know the details of Antler 2. It takes stuff and packages it up into a Btrfs subvolume ready to run the service. We then use Btrfs send, which actually takes, it's sort of like tar. It takes the on-disk representation of that package and turns it into a flat file that you can ship across the network. The merit of this is that Btrfs supports compression, and with Btrfs send, that compression is maintained. You don't have to uncompress to read the data. You don't have to recompress when you're writing it to the new location on a different machine, which is pretty exciting. This is only one of the many cool things about Antler. There's a talk about Antler, which last time I looked at the schedule was in the last time slot on Thursday. It's very cool technology. We then use a Kubernetes-style scheduler to ship the package around to wherever it needs to go. And then we use Btrfs receive, which writes the exact on-disk representation of the service's subvolume onto the Btrfs file system that's already on the service runner machine, and starts up the volume and all that stuff. Important to note here is that the service only ever writes to its own subvolume. There's no storing stuff on the root file system from within a service. And while we do stack multiple services on a single machine sometimes, each of them is confined. Even if they all need to write data, they all do it to their own dedicated subvolumes. So this posed some interesting opportunities for us to encrypt each of these subvolumes individually, while we have a bunch of existing security infrastructure. There's always room to add more layers of security, and we wondered if we could speed up securely deleting a service off of a machine and protecting one service's data from other services which might be running later. You could imagine that You have a service which writes some data to disk, shuts down, and then later on a malicious service happens to run on that same machine and tries to go exfiltrate that data by some way that it's figured out how to read the disk. By giving each of these containers its own encryption key, we might be able to prevent that specific use case. Of course, if both of those containers are running at the same time and somebody's figured out a container escape, you still have problems, but defense in depth. There are a couple of existing encryption options. The most well-known is obviously LUX, which uses Decrypt, which uses the device mapper framework in the kernel. It's what everybody uses. It's what Fedora uses. It's what's shipped by default everywhere. It's very well understood, very mature. We also have certain file systems which use the FSCrypt framework to provide data encryption to those file systems. You can sort of think of this according to the poorly drawn diagram I made. With LUX, you've got a file system stacked on top of some software-defined storage that happens to do encryption, which then talks to the drive directly. It's commonly used. It allows re-encrypting with a new key, as far as I know. You can change, you could ship a whole disk image with one key and then change it according to whatever the user of that machine wants the new key to be. However, this doesn't work perfectly if you want to have multiple users on that machine, each of which have their own keys, because you would need a partition per user, and as everyone knows, users have a habit of using different amounts of storage, never the amount that you want them to use. It also only works on whole devices because it's software-defined storage. You have to put your decrypt layer directly on top of whatever partition you need, so there's not a whole lot of flexibility there, but it does encrypt everything that gets written, which is very reassuring when it comes to encryption. You don't have to worry about whether you've got everything encrypted. You just know that it's all encrypted, whether it needs to be or not. FSCrypt is an alternative library in the kernel, which allows integration into specific file systems to do data encryption directly at the file system layer. As I understand it, this is what modern Android uses because it's efficient and only encrypts what needs to be encrypted according to their security model, namely the file names and the file data for each file. File metadata, such as xargs, xadders, or file sizes or stuff like that, does not get encrypted with FSCrypt. But you can have different keys for each directory tree, which is very useful when you want to encrypt different users' stuff with different keys. It doesn't allow mixing unencrypted and encrypted files, because you could imagine an attacker trying to stick an unencrypted file in an encrypted directory in order to get the user to accidentally execute something under an attacker's control. And when it encrypts file data, it does so based on the file metadata and the position within the file. So we figured that we should work on using FSCrypt with Btrfs to enable this usage. However, there are a couple of things that don't work quite so well with this model. One of the other bits of Btrfs send-receive that it transmits is reflinks. So this allows for a certain amount of data deduplication when sending across the wire, which matters at our scale. But with the reflink, you have two different files that both point to one on-disk extent of data. And they don't have to point at they don't have to have this data at the same position within the file. They could have this file goes and reads this extent for positions 0 to 1,000, and this file could use that extent for positions 1,000 to 2,000. So merely encrypting based on file and file position doesn't work very well for Btrfs. As I mentioned, our goal with adding encryption to Btrfs was to add another layer of defense and to allow fast subvolume deletion by merely deleting a subvolume key. This allows us to kill off a container faster when we know that we don't need its data anymore. Distributions using Btrfs might also care about this to provide individual keys for each user directory. You could imagine, I've heard it suggested, that perhaps a distribution could send an encrypted signed image out on a laptop to be imaged onto it. Laptop goes to a company, which then changes the encryption key going forward, writes whatever per company configuration needs to happen on there, then they ship it to the user, and the user then puts whatever per user configuration on there with their own individual subvolume key. However, there are a couple of difficulties that come up when you try to integrate these two models. With fscrypt, you want to have, you by default currently have one key per directory tree, but at Meta we have some delightful surfaces that themselves spawn surfaces inside of containers, inside of using subvolumes. So if you have one encrypted subvolume, and then you try to make more encrypted subvolumes within it, you run into issues because currently fscrypt wants all of the directory tree to have the same encryption key. There's also the bit about mixing unencrypted and encrypted files, which is not currently permitted by fscrypt. Our packages don't really need to be encrypted since everybody at the company can see their code just fine. Only the data written in a particular container really needs to be encrypted. And I already mentioned the difficulty with reflinks, where multiple files can point at a single on-disk chunk of encrypted data. Over the past year and a half, I've been working to change fscrypt to work with Btrfs. Btrfs will allow changing the key on a directory non-recursively, which allows use cases like putting new encrypted subvolumes with different keys inside of an encrypted subvolume. Currently, this only encrypts new writes to a subvolume. So if you try to, currently you can't change the key for data that's already been written. We hope to fix this one day, but it doesn't. For our particular package use case, it does not currently seem important. We also worked to allow fscrypt to encrypt data based on the extent of storing the encrypted data and the position within that extent instead of basing it on the file, so that we can get those reflink advantages that I mentioned. And we plan to have the key for each subvolume changed when a subvolume starts for the first time, and then we use our centralized key management service to distribute the key back to the container if we've shut it down and need to restart it. So currently, we're starting to figure out how it could work internally. We've been working on upstreaming it. It's hopefully on tap for Linux 6.7 in late November-ish, maybe. Hopefully. I really hoped that it would be upstream before this talk, but clearly it has not yet happened. However, you could build your own kernel and your own programs to allow using Btrfs with encryption from links that I'll upload the slides to the website in the future. It's very experimental at the moment. I don't trust my personal data to my encryption yet, but but for Facebook purposes, our rollouts are slow enough that we will notice things before they become issues. This will work with the standard fscript commands. fscript was recently packaged up for Fedora, so you should, and if you're using a different distro, it's pretty easy to build from source off of GitHub. It's got some pretty, it's simple to use. You just set up with your key. You use fscript encrypt to set a directory to be encrypted, and then you use fscript lock and unlock to make that data automatically visible, decrypted to you, as long as you've already loaded your requisite key. So it's very simple to use, very exciting. It's got, I think it's got great opportunities for future use with Fedora and perhaps other distros also. And I look forward to continuing to roll it out at Meta and hearing other people use it to keep their containers more secure also. So in the future, we plan to add authenticated encryption to this. Right now, Btrfs uses checksums to keep track of its data, but those checksums are on the encrypted data. This allows people to perhaps silently corrupt encrypted files, which you wouldn't notice until you tried to run your binary and ran into garbage. With authenticated encryption, you can't read the data unless it successfully decrypts to the correct value according to the authentication tag stored with the data. It's key dependent, very exciting, and should make Btrfs encryption even more resilient. Other file systems currently other file systems currently don't have an easy way of storing authentication tags, and this is a uniqueness of Btrfs that will allow it to store it more easily. You can also do authenticating encryption, I believe, with LUKS. I'm not an expert in LUKS, but that involves another device mapper layer, and I don't perfectly understand how those work together. So more alternatives, more flexibility should make security better. So yeah, thank you all for coming to my talk. Are there any questions?
So reflinking is within subvolume always. How does it work? Because you mentioned that the encryption is for shared extents, so
so if you could theoretically have two subvolumes with the same key, which would allow them to reflink a single extent into both of those subvolumes. However, other than that, if two subvolumes didn't have the same key, you wouldn't be able to reflink them together, or you'd have to have both keys loaded for both subvolumes if you wanted to reflink it. Yes?
Can you please repeat the question?
Thank you. The question was, can you reflink an extent from two different subvolumes? For our use case, we have single subvolumes for each surface, and so we don't do cross. As far as I know, we don't do cross-subvolume reflinks in the fleet right now. Does that answer your question?
yeah. So yes, the question is maybe stupid because I don't know how send receive works. If you were sending from an unencrypted source, then it wouldn't know that it needs to send just enough, just a reflink, it would need to send it whole data so that it can be really encrypted on the target, because it's in a, I mean, it could be there, but encrypted with a different key, so you cannot reflink it, and so on.
Right.
This is handled automatically.
So for our purposes, we plan to have unencrypted packages, which then either get written by receive equally unencrypted, and then we set an encryption key for future writes, or if you could set up your receive into a directory that's already got an encryption key set, and then the data being received would automatically be encrypted on the fly as we received it. However, in neither of those worlds would you get to reflink to existing data encrypted with a different key automatically. Mm-hmm.
So you said that only further writes are encrypted, so it's possible to have unencrypted and encrypted files in a subvolume.
Currently, the thought is that we'll use for the base image, we might use a common key, so you'd have to, instead of having it actually be unencrypted. But that's a point up for argument at the moment.
Thank you.
Are there any plans to encrypt the metadata of the files as well somehow?
Not at the moment. FSCrypt's model is that the file names and the file data are the important metadata to encrypt. There have been efforts to allow Btrfs to use other encryption in the past, but they haven't ever gotten to a point of usability. We do hope to make extended attributes be encrypted at some point, but we haven't done that yet. Mm-hmm.
So what about pre-compressed encoded writes in send strings? Are those only supported on encrypted receive?
Nope. So the idea is that the encryption happens after compression in all worlds. So you have your compressed extent coming in via Btrfs receive, and then it gets written to disk, and as part of being written to disk, we look up the appropriate key to encrypt it, encrypt that data going to disk, and then it comes back, and as it comes back, we look up the appropriate key and decrypt it before it ever gets to the decompression routine.
Hi. Have you mentioned, I might have missed it, in which case apologies. Have you mentioned Encryptfs?
I have not mentioned Encryptfs.
So probably you didn't like it. Apart from I think there's a page cache issue. Apart from that, what were the counter arguments?
In large part, my understanding is that FSCrypt was designed specifically to replace Encryptfs usage, precisely because of that page cache issue. So the idea with Encryptfs, in my brief study of the history of things, is that you have encrypted data written to a normal file system that doesn't know anything about encryption, and then you have something vaguely like overlayFS that automatically decrypts files accessed through it, but this results in double the page cache usage. The normal file system is going to read the encrypted data and store it in the page cache, and then Encryptfs is going to decrypt it to a different location in the page cache. So you end up using twice the memory for your I/O as you would otherwise. And that's fairly prohibitive in many workloads. Nobody wants to pay for extra memory. So FSCrypt addresses this by integrating directly with the file system to provide encryption decryption, as the file system is doing the I/O instead of above the file system. Cool. Thank you all for coming. I hope that y'all have an opportunity to try out Btrfs encryption sometime before next All Systems Go.